Good morning. We are Group 5. This is our fourth project for Material Science. I am Xander Craner.
I am Stanley Zhang.
And I'm Jeffrey Perez.
And this is our presentation on a thermal expansion problem involving two bars as well as Fick's first law. Today we're going to analyze a thermal expansion problem involving two bars, one iron and one aluminum, that are rigidly connected end to end. When both bars heat up, they want to expand, but rigid constraints prevent any change in total length. This creates internal stresses that we can calculate, and as well as Fick's first law, and see how diffusion flux and diffusion coefficients work. Assumptions. Before solving, here are some assumptions we'll use. The initial lengths of both bars are equal and are both 1 meter. The temperature rise is delta T equals 100 degrees Celsius. They have equal cross-sectional area, meaning the axial force and therefore axial stresses is the same in both bars. Linear elastic behavior is assumed first. Later, we'll comment on what happens when one material yields. Material constraints are given by these two values right here at 269 gigapascals respectively for iron and aluminum. Key physical ideas: because the ends are rigid, the total length after heating must remain at 2 meters exactly. Both bars would freely expand if unconstrained, but the constraint forces them to share a common compressive stress. We call this stress, and it will be negative for compression. Deriving the stress, compatibility and Hooke's law gives us the governing equation given right here, which must equal 0. Solving for common axial stress gives us this equation right here, which,
And now we'll look into the numerical results. What we get is negative 179.6 megapascals. So both bars experience the same compressive stress. For the final lengths, we compute using this formula. Our results show that the iron bar is 1.000302 meters, and it increased by 0.302 millimeters. The aluminum bar is 0.999698 meters, which decreased by negative 0.302 millimeters. The two changes cancel out, giving a perfectly unchanged total of 2.0 meters, as required by the rigid constraint. Now let's look at yielding consideration. The stress we found is about 180 megapascals, the typical yield strength. Many aluminum alloys are from 35 to 100 megapascals. Stronger aluminums are about 250 megapascals. Mild steels are between 250 and 400 megapascals. This means aluminum will often yield before steel in this scenario. If aluminum yields, the elastic solution is no longer valid. Instead, the common stress is capped at aluminum's compressive yield strength. Aluminum develops plastic strain to satisfy the total length constraint. The iron remains elastic unless its own yield is exceeded. Conclusion for thermal expansion. Heating two different materials under rigid constraint creates significant internal stresses. Purely elastic analysis predicts a compressive stress around 180 megapascals. Aluminum will likely yield first in most realistic applications. Once aluminum yields, the stress is limited by its yield strength, and the aluminum bar undergoes plastic deformation to maintain total length compatibility. For precise predictions, you need the exact aluminum alloy yield strength, and if needed, its hardening behavior. We will now look at Fick's law.
So for Fick's first law, in simple terms, the bigger the difference in concentration between two areas, the faster the particles will move to even things out. And it also states that the rate of diffusion is proportionate to the negative concentration gradient of the diffusing substance. So if you take water and oil, for example, it's not going to diffuse very well as opposed to something like water and salt. Right? And in our experiment, when we were doing the charts and graphs for everything, we can see that from 0 ps to 30 ps, it started to move to the right in equilibrium in space as the left side had no particles, as you can see in between these two parts. In the very beginning, all of it was concentrated on this side, and similar to how electrons like to move where negative energy is, these particles like to move to where there's empty spaces. So as you can see in these first two, we can see just how much the particles have spread out in terms of space. We also saw that in every 0.5 ps, either one or no particles move to the right. And at the end of 30 ps, we see that the particles are more to the right, then are slowly coming back to the middle to balance things out. So at the very initial, everything moved over to the right, but after a little bit, it started to balance out. Now, in our second experiment, we added a little bit less amount of particles to see just what happens with fewer atoms at the same temperatures. And as you can see from between experiment 1 and experiment 2, we have about half of the amount of particles. And with fewer particles in space, they ended up moving faster, similar to how we discuss things in material science. The more space there is, the faster a particle can move because there's less obstacles in the way. And it's shown here as well, where over 30 ps, all of the movement is much larger than what initially happened in the first experiment. And we saw more than 2 or 3 move to the right, and it reached equilibrium much faster than it did in the first equation and the first experiment. Now in our last experiment, we tried doing the opposite of what happened in the second experiment. So we can think of the first experiment as kind of like a dummy test, just to understand what would happen when we have a certain amount of particles. In the second test, we have a little bit less particles to see what happens. And in the final and third test, we have the most amount of particles. And in this third one, we increase the number of particles to 200 and reduce the temperature down to 50 K or 50 Kelvin. And this is a significant change. So as we all know, if you have more space, you have faster particles. You have less space, then the particles don't get to move as much. If you have a higher temperature, atoms like to move faster. Lower temperature, atoms like to stand more still. So since we increase the amount of particles and we decrease the temperature, it should also decrease the overall speed as well, which is what we noticed in our experiment. So in this experiment, we can see that with more particles and less temperature, it was hard for the system to reach equilibrium because the particles would move way too slow, and almost 3/4 of the particles were still on the left side and had barely reached the right side of the system. So it's like bumper cars. If you have a lot of things crowded up over here, they're not going to move until the very end when things are bouncing around, as opposed to this part when this guy can already move freely. And so we can see that in the third experiment, with more particles, things get slower. With less particles, things get a lot faster, and that goes for temperature too, but flipped. And now finally, we use that form to derive the diffusion flux equation, also known as Fick's first law, which is expressed as J equals to negative D dc over dx, where the rate of mass transfer per unit of area per unit of time, and it measures how fast particles are moving through a specific area. And this supports our data as we see in the effects of rate mass transfer. The way that we see it in experiments is that in each one, there was a rate of how fast the particles moved. Some of them were faster, some of them were slower, but all of them were based proportionately on how many particles there are and the temperature of the particles. So the data makes sense in the diffusion flux. And further going for the data in the diffusion flux, the diffusion coefficient is strongly dependent on the temperature. As temperature increase, atoms also gain more thermal energy, making it easier for them to hop between lattice sites. This led to a rapid increase in diffusion rate, and the temperature dependence is described mathematically by the Arrhenius equation, which is shown over here, D equals D naught exponential QD over RT. And here, D is the pre-exponential factor representing the maximum possible diffusion, so this is going to be the maximum diffusion. D naught over here represents the activation energy for the diffusion, which is the energy required for an atom to move from one side to another. Q is the gas constant, which is just a constant, and RT is going to be the absolute temperature. And because of the exponential term, even a modest increase in temperature causes a dramatic rise in diffusion, and this is why processes such as heat treatment, carbonizing, and grain growth occur more rapidly in an elevated temperature. And this again shows support in our data for the experiment, since in experiment 3 we had much lower temperature, which made our particles go slower. But when we went to experiment 1, which we had 300 Kelvin, which is close to standard, we see the particles move way faster than it did in experiment 3, proving that the diffusion coefficient of temperature dependence supports our data. And thank you very much.